Hello and welcome back to the crypto engineering course. Today we will be talking about a particular aspect of engineering that we typically underestimate the importance of, and this is usability. So I want to again briefly reflect on the differences between crypto engineering and the wider field of security engineering. And one of the things that perhaps we would be missing out is this key aspect of what people also call the human factor. The very simple fact that people who develop programs, well, they are just ordinary people and they can make mistakes. Users of programs, of course, can also make mistakes, and all of these mistakes are potential security problems, which means that we need to have at least some awareness of why people make mistakes, the type of mistakes people make, and also what contributes to the frequency of making mistakes. So perhaps when we develop something that is then eventually used by others, we develop it in such a way that A, we make less mistakes ourselves, and B, we help others to use what we have developed correctly. And what we're going to think about today applies equally to specifications, documentations, pieces of software, and also descriptions of hardware. So crypto versus security engineering. I encouraged you already after the last segment that you would go away and perhaps read through the first chapter of Ross Anderson's book to get a little bit of a wider perspective on what really security engineering all entails, and perhaps what the kind of significance of crypto engineering is in that wider field. So I think one of the perhaps most important takeaway messages is that we as engineers typically think about a system in terms of its technical components. But although they are, of course, incredibly important, they are some of the fundamental building blocks typically, they are really just components, and any larger system is only as secure as is its weakest link, which means that really every single component, whether it's technical or not, deserves equal attention. So other components are users typically, but users' behavior is also governed often by the rules and regulations that they have to follow and how they are incentivized in their behavior. So today's kind of subject really is to look at this, what people often call the human factor. So the fact that a really important aspect of any system is that of the human kind of user. And it's kind of interesting, really, because most traditional cryptography courses start by considering and reviewing and reflecting on some key principles that were put forward by a very early cryptographer called Auguste Kerckhoffs. And I'm sure you will have heard of his name and you will be familiar with some of the statements that he has made. And in fact, he put forward a number of principles, and typically, and I'm no different here. When I structure a cryptography course, I will review one or two of his principles. I will never go through actually all of them. And there's one key principle which I tend not to list for a crypto course, and this is the one that roughly translates as follows. Lastly, given the circumstances in which it is to be used, the system must be easy to use and should not be stressful to use or require its users to know and comply with a long list of rules. This is really, really important, isn't it? And it's really, really curious that already one of the earliest cryptographers clearly recognized that usability is an absolutely key criterion for any kind of cryptographic system. And I would argue that this really applies then to any kind of security-related system. And in a way, it should be completely obvious that if a system that is complicated to use, or that annoys you, or that really inconveniences you, you will not use very long. Typically, you will just ditch it and use something else, or don't use any security mechanism at all. And then there's the next obvious statement: a security feature that isn't really used in practice can't really contribute to security. So it is crucial that we at least consider it to some extent. So usability is really obvious in the systems area, in the crypto component area. So suppose we are not considering anymore I don't know, just a larger system where there is immediately a user to be kind of considered, but we're just considering a subsystem, an API that is called as part of a kind of larger system. Should this principle apply still? And I would argue, yes, I think so. If a crypto component has poor usability, then people who kind of depend on it and build on it will either use it wrongly or use it as sparingly as possible. And perhaps this is also a good opportunity at this point for you to perhaps pause the video and just take a few moments and think about, really very specifically, what crypto or security systems have you used yourself in your daily life? And how would you rate their usability? You may think about email encryption, file encryption, or maybe other systems like the online banking system that your bank has decided that you will use. Or maybe, I don't know, the AAU door card system. Anything really that you are interested in. Just pause for a moment, think about it. How do you use it? And how do you feel about using it? Is it convenient? Do you feel you benefit from it? Or what's actually kind of your experience with it? And once you've done that, just continue with the video. So usability as a kind of key requirement, although it seems so obvious, has kind of entered the field into the security field really quite late. But outside of security, usability has always been a very, very prolific research area. And if you're interested in sort of which corner of computer science you would need to look to find interesting results about usability, then you need to go into a field called human-computer interaction, or short HCI. And in the various conferences in this area, so CHI is one of the largest ones, CHI, and they have long championed the idea of really a systematic study of checking how users and computer systems interact. And it's really a very interesting community because they're computer scientists and psychologists. Typically, they work together to kind of find interesting and useful methods to evaluate the usability of computer systems. As I said, this kind of research area has kind of come into the crypto security community actually fairly late in the day. And it was kicked off by a now, I would say, absolutely infamous paper. The paper is called Why Johnny Can't Encrypt. And you should really go out, find it. It's publicly available, and have a look through the experiments that they run. So famously published by two researchers called Witten and Tigger, and they published this at Usenix 1999. So this is really late in the day. It's in fact a coincidence. In the same year, one of the most now famous implementation attacks was also published, namely the power analysis attack by Kocher et al. So a lot happened in 1999, really. And they carried out a usability experiment. So they were curious about the usability of some security or encryption software. And so they kind of scouted a little bit what was actually available on the market, what they could use and they could test. And they looked at a number of things and kind of discounted most of the products that they found because they concluded right away that they are not usable at all. But one of the products that was sort of reasonably well designed and had in fact even a computer, had in fact a nice graphical interface, it wasn't command line based, was PGP 5.0. So they wondered if college students, so not beginners actually, more seasoned college students, would be able, with the PGP software and the documentation that it provides, to successfully encrypt an email within 90 minutes. So they were keen to sort of ensure that the students weren't already budding cryptographers or security engineers, but sort of ordinary from all kind of subjects, so areas of study. Where would they be able, as fairly intelligent, technologically savvy people for the time, would they be able to encrypt a simple email? And their conclusion was that based on the results of our evaluation, we conclude that PGP 5.0's user interface does not even come reasonably close to achieving our usability standard. it does not make public key encryption of electronic mail manageable for average computer users. So that's a quotation from their paper. That's really quite damning. So, but what was their definition of usability? And I'm putting this here on the slides because I think that the usability definition that they use isn't extremely specific to the use case of PGP 5.0. I think you can extrapolate from it a number of useful usability requirements that are broadly applicable for a wide range of applications. So what they formulated in their paper was usability, or security software is usable if the people who are expected to use it, firstly, are reliably made aware of the security tasks that they perform, are able to figure out how to successfully perform these tasks, don't make dangerous errors, and are sufficiently comfortable with the interface to continue using it. So it's not just that you know what you're going to do, you also should know how you're going to achieve your task. You should have enough explanation from that, or enough understanding of the why, that you don't make really dangerous errors, so kind of don't achieve in a way what you're trying to do. And that it's not so tedious that you'll only do it ever once. So ideally, you would do the task again. So I think these 4 kind of points: know what you should be doing, know how to do it, don't make dangerous errors, and do the task again. This is really broadly applicable to any kind of component that you're designing for somebody else to use or to embed. So really, very simply speaking, you can kind of rephrase these 4 things into the what, how, and why questions that we often use when we try and explain something successfully to other people. There's a very famous TED talk by Simon Sinek, which is called How, What, and Why. And it gives you kind of basic outline of how you should be structuring an argument or a presentation such that you're engaging your audience. And really, what you're doing as a developer of a product of some sort, now again, whether this is a documentation, specification, a software, an API, a piece of software, a piece of hardware, it doesn't really matter. You do something that somebody else is meant to use and to be in a way interested in, then you should be covering these 3 aspects. What am I meant to be doing with the thing that you're giving me? How should I be using it? And why actually am I using it in the way that I'm using it? So that goes some way of ensuring that people don't use it wrongly, so don't make mistakes. So addressing the how and why in a suitable manner can help minimize errors based on either misunderstanding or lack of awareness of the risk that is kind of involved when you're either using this component or not using it correctly. So if you think about the example that the researchers studied, so the encryption, email encryption with PGP, one of the things that you really want to minimize is exposure of the private key or the secret key. And so they considered it as a complete security failure if people accidentally send out their secret keys and not their public keys. And it happened quite often. And I should be saying at this point that in many of my previous courses that I taught in England, I taught something for first-year students. And also there we had this little challenge for them at the beginning to actually encrypt an email, not using PGP necessarily, but already using some Gmail plugins or something like that. And even there, where I would say the user interface and the usability is so much better, typically about 20% of all the students emailed their secret key out to other students. So how come that people so readily make mistakes? There are in fact different types of mistakes that people make, and all of them are somehow related to a limit of our capability. So if you ask why people make mistakes, then the psychologist's answer will be, well, we are most likely to make mistakes when we are given tasks that exceed our capabilities. So what are our capabilities? So for instance, humans can focus their attention primarily on one task at a time. It's a myth that people are good at multitasking. It's also a myth that women are necessarily better at multitasking than men. There is a certain practice that you can do in order to become better at multitasking, but when it comes to really, really crucial tasks, You do not want to be multitasking. Another capability or a limit to our capability is how much attention can we pay to something. And this relates to something called alarm fatigue. So if you have some product that constantly tells you something is wrong, think about a faulty fire alarm. So something that we have installed typically in our homes that detects if there's gas or something else. If there is an alarm that you have sort of mounted close to the kitchen area and it constantly beeps, of course at some point you will simply ignore it. And this is called alarm fatigue. And it happens all the time with all sorts of notifications. So people stop paying attention to them if they're not reliable. So you shouldn't alert users too often to something. Another limitation is our memory. And there are two types of memory. You can sort of make even more fine-grained distinctions, but for our purpose, two types are good enough. So there's the short-term memory and the long-term memory. And the important thing to be aware of is that if we need to memorize something, then for a while this item, this thing, whether it's a number, a word or something else, needs to go around our short-term memory for a while until it actually gets put into the long-term memory. So if we have lots of applications that all require different passwords, and we have silly rules such as we always need to have a new password for every single application, and we can't write it down or something like that, then we have a real issue because we don't practice these new passwords often enough, so inevitably we will forget them. And if you're using software like Signal or WhatsApp or something like that, you might notice that sometimes these kind of newer products, they keep reminding us of, I don't know, a PIN or a password or whatever by sort of prompting us to enter it again and again every few days. And this is not because there's a security concern, this is simply to help us with our memory. Another capability that comes, of course, with a limitation is that human behavior is essentially goal-driven. We do like to go for random walks around, but most people will most of the time walk to a place because they want to achieve something. So if we take this idea of goal-driven behavior and map this to a piece of software, hardware, whatever, then we're probably not just using a piece of software because it's so enjoyable, but because we want to achieve something. And sometimes we have to use or we have to express a certain behavior as part of another goal that we are having or that is being given to us. So if security software or security products stand in the way of achieving another important goal, they will simply not be used, and you might as well just not introduce them at all. And then finally, if we do something really often, so if we've got a task that is very repetitive, or if we've got a task that we do on a day-by-day basis, or maybe even more often than that, then eventually we stop thinking about that. Our brain is clever enough to optimize these kind of things, and they will just become somewhat automatic. And of course, this can be really dangerous. If we are doing a task that is related to an important security functionality, we should in fact always be paying attention, but if we're doing it so often, then most likely we will not pay attention anymore. So we make errors when we are given tasks that exceed our capabilities. And it turns out that basically all of the mistakes that we make are somewhat predictable. And James Reason in some of his research showed that, and he showed that you can categorize mistakes into sort of two types: latent failures or active failures. So latent failures are due because of organizations and external conditions, and active failures, they are sort of more due to something going on in humans' brains. And typically it's a combination of both that kind of mean that really bad things happen. So individual factors of latent failures is, for instance, fatigue. If we are already tired and we still have to carry on with something, we are very likely to make a mistake. If we have not much experience with something, we are more likely to make a mistake than when we are already very good at something. But of course, if we're very experienced with something, then it might be that we're already doing things automatically, which again increases our likelihood of making mistakes. And another individual factor is in fact risk-taking. So some people, they are more willing to take something easy or try something new out than others. And this is in fact a type of risk-taking behavior which can also be attributed then to making more mistakes. Human factors include the limitation of memory, but also common habits or assumptions that we make about something which are in fact not always true. Task factors are part of latent failures. So this is again time pressure or maybe high workload, having to multitask, monotony and boredom contribute to making mistakes. Also uncertainty about who's supposed to do what. Often that can also be in relation to social norms, for instance, that we have to observe at the same time. So for instance, if you consider the university as an example for many workplaces where you have a badge that allows you to gain access to certain buildings, then obviously this badge and the door entry system means that only legitimate users of a building are supposed to enter. At the same time, our social norms tell us that if we are opening a door and there's somebody behind us, then we will keep the door open for them. But does the other person also have a badge and is actually allowed to enter the building? Perhaps not always, but our social norm would suggest if we essentially slam the door in front of them, we would be extremely rude. So very few people will actually do that. And then other work environment factors are listed here, like poor equipment, poor information, and constant changing of rules and procedures. And perhaps we are now living in a great time to experience that all because of the kind of changes in the condition around the COVID-19 spread. We regularly get new rules and regulations, and I would say a large majority of the population are utterly confused sometimes about what they're supposed to be doing and what they're not supposed to be doing. So obviously people are much more likely then to get something wrong. A example that should illustrate how goals that are imposed on us sometimes can conflict with good security behavior is one where you have, for instance, a shop and a cashier, and they would have to type in an ID or a PIN password into their till before they can actually operate it. Now the idea is that obviously only specific people are allowed to use tills, and that makes a lot of sense, but typically shops don't have that many staff these days, so people at the checkout might also be expected to help customers on the shop floor. So if they have to rush back and forth, and then every single time they have to log in and they also should be logging out, then you can imagine that it's very quickly will become a real hassle for them. So if all what is needed then to kind of do a checkout, then perhaps the staff would agree that it would be much easier if simply one person logs into the till and then it simply remains open. So that of course would be really bad security behavior, but absolutely understandable when it comes to the task that people are supposed to be doing. So perhaps sometimes you can change such security behavior by also changing the incentives. So for instance, you then modify the system such that each worker has some form of also competitive payment, where the more that they personally sell, the more they somewhat get on top of their perhaps base salary. Then they would be much more incentivized to log in and out, because obviously you will not be happy for somebody else to log in the morning and then everything that you in fact sell later on is actually logged to their login. So incentives play a big role of having people behave in certain ways. Let's focus a little bit more on errors that are based on misunderstandings, whether they are because somebody simply really, hasn't really understood what they're supposed to be doing, or whether the instructions are very kind of different and ambiguous, is often really completely irrelevant. And I would say that the latter point, that instructions are difficult in the sense that they were clear to the person who wrote them, but they're unclear to everyone else. This, I think, is one of the most frequent reasons why things go wrong. And I took a few photos, and I've got a few kind of things that I gathered from some of my psychologist friends in this area to illustrate the point. So here, for instance, is a typical door exit system that you would find at many British universities. You have got a green button that you have to press in order to get a secure door to open for you so you can exit. But you also have a green little square often underneath, which is the emergency door opening system in case of a fire. So you want to press a green button to exit, yes, but which one is not so clear. And here in this particular place, people had to add some additional instructions because otherwise students would constantly smash the emergency door release, which is related to the fire alarm system. And if you look at it, really at these two buttons, then both of them say, in a way, you need to press this in order to exit. And perhaps most of us would think, well, I press the button where I don't have to smash the window. But a large proportion of students, in fact, were willing to smash the window to get this door to open because they were trying to get out, really. So the additional labeling that you can see here with the smiley faces really did the trick. This here is something that is, I would say, particularly interesting. So somebody went absolutely bonkers with signs here, and you could sort of try and think it through, really, where actually all these signs together, so jointly, still make sense. So you can see that there's perhaps some over-labeling going on, because if we take, for instance, the one-way sign, which is sort of at the bottom middle here, then it tells you very unambiguously that you can only go to the right. But of course, there's also the question, well, could you go straight on? And here it's then explained in a very complicated manner that, well, you're not allowed to go left, you're not allowed to turn around, so probably this means you can't, so you may still go on straight, but then it says wrong way, so this takes away your last option. And of course, here in our kind of area, you would probably solve this with a blue and white arrow sign around one, which kind of tells you which is the only direction you can go. But here you needed quite a few signs to express that you must turn right here. It's also fascinating to see how they express that there is a speed limit here. So you've got a speed limit of 25. You also have speed checked by radar. And one wonders whether both of these signs are really necessary. I think one of the really interesting things is that there is this green kind of sign which tells you the park is to the left. Unfortunately, you really shouldn't turn left. And then we've got things that there are people running away from something, seemingly. So this is a sign that isn't really used, I think, in our area here. For some reason, they also tell you that you're not supposed to be skateboarding and other things at the same time. So, I mean, there's an awful lot going on. Ambiguity is really, I would say, the core of so many mistakes that we make. So this signing here is obviously very well meant. You're supposed to find out in which direction you go for the rooms 101 to 113 and for the rooms 114 to 128. The question is just, how do you read that sign? Is it that the right arrow belongs to the rooms 101 to 113, or is it that it belongs to the rooms 114 to 128? And I actually don't know where this was taken, but I believe it's some other British university, and I have no clue how students actually figure it out, or other people. Presumably you simply go in a circle, which is what I used to do quite often at my British university, because the building was like a rat maze. And these kind of things, they are, as we can see, available in many situations in real life, but they are also part sometimes of the specifications that we write. So an example that I found you that really relates directly to cryptographic software is when you look at the specification of the data encryption standard, or DES. And it's something that perhaps is slightly more tied to it than to other algorithms, but in principle it's not just that the DES description is difficult, but that we have certain conventions which are sometimes difficult to understand or to realize. And this is, so suppose you have got some notation that explains how plain text arrives that you're going to encrypt. And in the case of DES, you need to sort of split up things in the left and the right half, and then you need to deal with the bytes sometimes. Now the question is, how do you label things? Do you kind of label things from left to right? So the kind of big endian notation, so this kind of how do you label things from left to right, is called also endianness. Big endian means that the highest byte you write first when you write it down. So it's like when you write things in a positional number system, the leftmost number represents the highest kind of term. Or do you write things that the lowest byte comes first? So simply the other way around. So quite often when we write things down, we always assume that we use a sort of a big endian notation, but in DES, the specification assumes exactly the opposite. Now there are some computer systems which also sort of internally label things in little endian, but most of them don't. So if you're implementing this, then I would say most people at some point will have scratched their head of how do you now really number things, and how does that relate to the kind of convention that your computing architecture really has. And if you want to sort of, I don't know, read a little bit around it, or perhaps just have a little chuckle at the kind of despair that other people had, then you could follow the link that I'm providing you here. So this is a quite lengthy conversation by some very, I would say, senior people within the crypto scene who are discussing what the endianness really means in the DES specification and how you should apply it in a real kind of implementation. So, and I would really say that the people who are writing in this thread, they absolutely know what they're talking about, and still even they struggle to understand each other and to agree on how to really read the same piece of specification. So I think that in itself is a sign that perhaps it's not as clear or as simple as it could be. Another example that now really concretely relates to the sort of crypto side of things is the OpenSSL API, which has been again a source of great despair for a lot of people. So suppose you want to encrypt something, and for some reason somebody has told you that OpenSSL would be a really good way to do that. So you could try and download OpenSSL and use that to actually encrypt a file or something. So you would then be wondering, so how do I do that? Is there somewhere an encrypt function perhaps that will do the trick for me? So there is a sort of simple encryption function, but it still requires quite a few parameters actually. And have a look. So I provide you here with a link of what actually the syntax here looks like. And this documentation that they provide here is really not super easy to read. So there are, if you then sort of get a bit desperate and you sort of Google for, well, how do I use OpenSSL to encrypt a file, then you'll find a bunch of tutorials. And I just picked one of them and looked into it when I prepared for this lecture. And again, I'm providing you here with a link to it. I would suggest that you pause the video now, follow this link, and have a read through this tutorial and think about whether or not you think what it says is particularly sensible. So I think there's a problem with that tutorial. Pause the video now, read through it, and think about whether you can spot the problem or not. Okay, so if you've read through the tutorial, you might have noticed that the writer says that in CBC mode, which is what a lot of people would still use as the standard mode of operation for encryption, there is this IV, and if you choose it freshly, it will add to the security of your encryption. Now, I think this is not correct. Yeah, the IV does not add to the security; it makes the security. If you do not have a randomly chosen IV for CBC mode, you have no security whatsoever. You might as well not do anything. So you can see that this tutorial, in fact, makes you believe that the IV is in a way optional, whereas for a cryptographer, it is absolutely not. Now, this is a problem in the tutorial, but in fact, it has been perhaps come from the fact that in OpenSSL, the kind of function call for CBC encryption was perhaps also, I would say, slightly ambiguous. Namely, if you called ALG, so that would be AES or DES or whatever, then underscore CBC underscore encrypt, then this function, in fact, did not use the CBC mode correctly because it would not update the IV that was currently held in an IV field somewhere. And as I said before, the having a random and freshly chosen IV is not optional for CBC. It is absolutely mandatory. So that you have a CBC mode encryption function which does not require you to sample a fresh IV, I think is a bad mistake. And strangely enough, within OpenSSL, within that library, there was another function called ALG. So again, you have to substitute this for the algorithm of your choice, so maybe AES, underscore NCBC, underscore encrypt. That would actually enable you to also use a fresh IV. So I would say this is very, very confusing. And no wonder that a lot of people would use this incorrectly. So we looked at now errors that are based on misunderstanding because a description isn't sufficiently precise and understandable. But there are also errors that we make because we take risks. And one of the questions perhaps to a little bit reflect on is, why do we take some risks? What's the benefit? Are you a risk taker? Do you feel quite happy about trying something out, something where you're not quite sure whether it's really safe to do or a good thing to do? So why do people take risks? And again, psychologists looked at that in great detail, and a person called Reber defines it as follows. It's an action that jeopardizes something of value. So it's something where we perhaps have some emotional reaction to it. So a potential factor that contributes to risk taking is that because we jeopardize something, we might also attract some form of feedback, some form of reaction. And obviously, many of us will prefer a kind of a positive feedback. So if people tell us we've done well, that's certainly nice to hear. But any kind of feedback, in fact, invokes in most of us an emotional reaction. And also aversive feedback provokes some form of reaction. And sometimes excitement. And excitement can be interesting and pleasant. And think about, for instance, watching, I don't know, a scary movie. You are scared, you are shocked sometimes, your body feels excited, there's a real reaction to what you see, and you do it again. Or, I don't know, in some entertainment parks, you do a crazy ride, you feel exhilarated afterwards, although you have been really frightened. And perhaps the reason for that is because it doesn't matter whether we have positive excitement or negative excitement. Our body always releases a hormone called adrenaline, and this is associated with euphoria, and in fact it's slightly addictive. So typically people fall then into a cycle where they are sort of, there's a stage before the excitement, so you're already looking forward to it, then you have got the thrill during your excitement, and then afterwards there's some form of euphoria. And this can be really gratifying, and some people really want to have this again and again and again. And if they don't get it by positive feedback, they will be happy also to get it via some negative feedback. Another way of thinking about risk is that perhaps it relates actually to our personality. So it's not just learned behavior, it's sort of more inherent behavior. And in fact, even kind of personality tests, which kind of take into account or try and find out what kind of risk-taking behavior you are more likely to kind of display. And related to both sort of a learned behavior and an inherent behavior is also the idea of risk homeostasis. And here the idea is that if we try and make a situation really, really safe, then many people, in fact the vast majority of people, will be willing to take more risks in that situation. So a really good example is when in the late, I don't know, 1970s, 1980s or whatever, the wearing of seatbelts was made compulsory in cars. People started to drive much faster. We make driving safer because we wear seatbelts and people thought, okay, now we can drive faster. And perhaps there's something of that also going on when we develop software, when we develop specifications. The more tools that we have that help us to check for mistakes and so on, perhaps the less attention we pay. So I think it's really well worth being aware of that, and whether or not you think you might be slightly influenced by the fact that, I don't know, if you code in Java, perhaps you feel, because it's a safer language to use, that you are a bit sloppier in your coding. Whereas if you code in assembly, where you can get things badly wrong, or C, where you can shoot yourself quite easily, you pay much more attention. So I want to finish this off with another look at mistakes that people make that are very much related to crypto implementations. And for that, I'd like to draw your attention to a super recent paper. In fact, something that has just been published online, and that will appear then only in a while, and the link is here to that paper, and it's about a tool that people developed. It's a tool, so similar tools have existed before, and this is kind of the newest iteration of the same experiment. It's called CryptoLogger, and it's essentially a tool that you can use to scan crypto implementations for typical vulnerabilities. So for typical mistakes that developers make. And researchers designed this tool and then applied it to a large range of applications on, I don't know, I think it was an Android app store or something like that. So they found loads and loads of apps that were really appalling in terms of their crypto use, and they let the app developers know, and the vast majority of app developers did not care at all. So, but what kind of things did they scan for? I do not want to read out every single rule that they check, but I just want to draw your attention to some of these rules, because I hope that from your previous education you would see that they are kind of sensible to check. So first of all, if you think about crypto primitives, you want to ensure that you use state-of-the-art primitives. So things from which we know that they're okay, rather than things from which we know that they have already been broken. So broken hash functions, plenty around, right? MD5 is deeply embedded everywhere, and you really shouldn't be using it. But there are even older ones like MD2, MD4, you also shouldn't be using that. And also SHA-1, perhaps you should be phasing out. So they scanned for this. And the same, of course, is for encryption algorithms. You shouldn't be using DES. If you have to use DES, please use triple DES. RC2, RC4, IDEA, all of them are badly broken. So they would check for that. So that was their second rule. Then, of course, a block cipher, even if it is secure, does not give you yet a secure encryption scheme. You have to use a secure mode of operation in the right way. So you shouldn't be using ECB mode. CBC mode, also best to be avoided. Then we have got the next issue with how do you sample encryption keys. So if so you should be updating keys, so having static keys for encryption, bad idea, they checked for that. Badly derived keys, so non-standard key derivation functions, you should be checking for that. Badly derived or constant IVs, they checked for that. Reuse of IVs, they checked for that. Sold for hashes or key derivation, they checked for bad randomness here, and so on. So you can see sort of the typical things that we definitely covered largely in the cryptography course, and I hope you would have covered also in system security. They kind of simply checked for. And then it sort of went on a bit broader, sort of weak passwords, blacklisted passwords, reusing the same password, bad PRNGs, padding oracles, we looked at that in cryptography, and not using HTTPS, just using HTTP, raw RSA, raw LGAMAL, so raw anything, and so on and so forth. So they checked for all of these rules. And I would say that this is also something that if you were to do a code review, you would need to look at, for instance. Now over to you. Part here, I would say, have a little bit more of a look around about psychology as part of usable security. Then there is an interesting chapter in a large body of work which is called CyBOK. So cybersecurity system of knowledge or something like that. I can't quite remember what it was called, or body of knowledge actually. And there is a chapter on human factors, and I provide you with a link here. And then also from Ross Anderson, there is a chapter in his book about psychology, which is perhaps a bit deeper. And I would leave it open to you if you wanted to really read into this. But at least I would suggest watch some of the videos, and I give you here the starting one to, I think, the 2 or 3 videos that he has produced in terms of the psychology of security.